oil would no longer be useful. Natural gas would no longer be useful because this would be the ideal energy source, the cheapest possible energy source, involving only water. And so if this were real, all the other sources of energy were irrelevant.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective on important societal issues.
Produced by Soapbox Media.
Hello, and welcome to another episode of The Rational View. In this episode, I start my investigation into the cold fusion controversy. In 1989, Pons and Fleischmann announced in a hastily convened press conference the discovery of a new clean energy source that would revolutionize power grids and save humanity from climate change. They had measured the production of excess heat and neutrons in a room temperature electrolytic reaction using heavy water and a palladium cathode. It shortly became evident that their claims were not entirely correct. After many attempts, it was discovered that their experiment could not be replicated, and mainstream science summarily dismissed cold fusion as pathological science. Despite this lack of acceptance, many have continued to try to replicate their work and strike it rich. Now, after more than 30 years, a pattern of unexplained anomalous results seems to be emerging from the rubble. Is there something to the newly renamed low-energy nuclear reactions field? To answer that question, I'm interviewing an expert who's been involved in reviewing the work in this field since the very beginning. If you like what you're hearing, please press like on your podcast app, share it with your friends. Come join the discussion at my Facebook group, The Rational View. Edmund Storms obtained a PhD in radiochemistry from Washington University, St. Louis, and is retired from the Los Alamos National Laboratory after 34 years of service. His work involved basic research in the field of high-temperature chemistry as applied to materials used in nuclear power and propulsion reactors. He presently lives in Santa Fe, where he's investigating the cold fusion effect in his own laboratory. An authority in the field, he's published 2 books, over 100 papers, and 4 complete scientific reviews of that field over the years. In May 1993, he was invited to testify before a congressional committee about the cold fusion effect. In 1998, Wired magazine honored him as one of the 25 people in the U.S. who is making a significant contribution to new ideas. He was awarded the Preparata Medal by the International Society of Condensed Matter Nuclear Science and honored as Distinguished Science by University of Missouri. His large collection of literature about low-energy nuclear reactions was used to create the website www.lenr.org, where information about the phenomenon is available. His recent work is focused on understanding LENR and making the effect reproducible. Dr. Storms, welcome to The Rational View.
Well, thank you very much.
So you worked as a radiochemist at Los Alamos National Lab for 34 years. You published over 50 papers and a book on that topic. And you're a well-regarded mainstream scientist at a high-profile research lab. What prompted you to get involved in cold fusion?
Well, I was working on materials that were of use to produce propulsion, nuclear propulsion in space, and then also later nuclear energy in space using the ordinary fission technique. And when Pons and Fleischmann made their announcement, Los Alamos was incredibly interested in this claim, because if they were right, if this source of energy was real, then this would be the ideal source of energy for use in space and for use in space travel. And so Los Alamos became really excited. I mean, the entire laboratory got involved. Numerous people attempted to replicate what Pons and Fleischmann had done. It was meetings held weekly, attended by hundreds of scientists. Great enthusiasm was shown. Both Pons and Fleischmann came to the Los Alamos and gave talks describing what they were claiming to do. And so I actually got interested because I had access to equipment and knowledge that made it possible for me to replicate what they were doing. I also knew of them as scientists and highly respected them as honest, creative individuals. So I set up to measure tritium. The group I was in studied tritium for the hot fusion program. And so we had available to us the world's experts on tritium measurement and tritium behavior. And so this was the ideal situation for me because we knew tritium, we knew how to deal with it. And the anticipation at the time was that tritium would be one of the nuclear products, since tritium is one of the nuclear products of the hot fusion mechanism. And at that time, we didn't really understand that an entirely different, totally unusual mechanism was operating in these materials, having no relationship whatsoever to hot fusion. But lucky for us, that mechanism also made tritium. And so I was able to make some tritium, and so did a lot of other people at the same time. That pretty much convinced me that this was real. And it convinced people at the laboratory it was real. And a number of other people, Tom Claytor was one of the others that made tritium by a different technique. I was using electrolysis, the classic Pons Fleischmann technique. Tom Claytor was using a gas discharge technique, which he continued to use and was continually successful for many, many years. So the evidence for tritium production was very well established at Los Alamos. The only problem came later when the DOE essentially officially concluded that Pons and Fleischmann had made a mistake. And so all work at Los Alamos on the cold fusion thermometer was shut down.
Can you talk a little bit about the initial results or lack of ability to reproduce Pons's and Fleischmann's results? Obviously, the scientific community kind of declared it as a dead field. Some people thought of it as pathological science, and yet you say that there were results where you were getting tritium. There were sporadic results of anomalous stuff happening there. How certain were those results, and were they overlooked by the community, or what happened there?
Well, this was a fantastic study in psychology and the way in which the human brain operates. Discoveries, of course, have always suffered from rejection early on. So this isn't new. The magnitude of this rejection is new, and the duration of the rejection is new. But the rejection came about to some extent from two basic reasons. One with a certain amount of integrity and the other without any integrity whatsoever. The ability to cause any kind of nuclear reaction within a chemical system was impossible. I mean, anybody that studied nuclear chemistry understood that what that claim was completely impossible. It could not possibly happen. The understanding of the relationship between chemistry and nuclear interaction, the interaction with the nucleus, was fairly well established thanks to the hot fusion program. And so we knew what was possible, and this was not possible. Also, if it were possible, you would expect to see the nuclear products that people had identified coming from the hot fusion program. They were absent.
Yeah. I remember one of the biggest refutations was the lack of neutrons, right? Because if the power had been created by hot fusion, the neutron flux would have killed the researchers. And I remember that refutation, is very held up as, they obviously don't know what they're talking about. It was, some ridicule was involved in that.
Neutrons are really easy to detect. And so many physicists and many laboratories have the ability to detect neutrons. And so all of them essentially set up an electrolytic cell with some palladium in it and put their neutron detector in front of it and waited weeks and nothing happened. And first of all, they knew that neutrons had to come out. No neutrons were coming out. So therefore, this was not correct. This was not actually happening the way Pons and Fleischmann claimed it to happen. Simultaneous with that legitimate reason for being skeptical was the awareness by the people in charge that if cold fusion were real, the hot fusion program was toast. There's no reason to put any more money into that. And in fact, all the energy
spending billions on that, right? That was huge.
They spent a huge amount of money on that. But what was worse, oil would no longer be useful. Natural gas would no longer be useful because this would be the ideal energy source, the cheapest possible energy source, involving only water. And so if this were real, all the other sources of energy were irrelevant. And the people in charge are not stupid. They realized that. And in fact, the president at the time was Bush the Elder. And of course, he was very strongly involved with oil. And he could see the writing on the wall. His whole livelihood could be in jeopardy if this were real. So there was a certain incentive on the part of people who were in the power structure and had a relationship to the normal energy sources to try to diminish the possibility of this being a competitor in the future. And that was easily done because of the natural conflict between what people expected to see and what they actually saw.
Mm-hmm.
Now, a few of us, mostly as a result of luck, this was not easily produced. The conditions within the material are not easily created. You have to create very special and unusual conditions within the material. Ordinary material does not work. And most people got their hands on ordinary material and they tried to make it work and it didn't work. And we now know why it doesn't work. And we know that you just don't use ordinary material. That just is not the way to do it. But if you have material that has been treated in a particular way and has certain characteristics, it will work every time. We didn't know that then. Mm-hmm. We do know that now. Now, in the interval, a lot of that knowledge was accumulated. It was denied access to many of the journals, so many of the scientists never had an opportunity to learn anything about what was discovered. So a lot of the rejection right now is based totally on ignorance.
So yeah, you've published several scientific reviews of this field over the years. And as you say, most of the work was not being published in mainstream journals at the time. They were kind of shut out of Nature and Science and had to publish in what so-called fringe journals in a lot of cases. And they held their own independent conference, I believe, soon after the announcement. There was an annual conference that they would hold to discuss the research. So the standards of peer review for their annual conference have been scoffed at by critics. The lack of skepticism, of course, if you're under attack by the mainstream, obviously you don't want to add fuel to the fire. There's kind of a circle the wagons mentality that happens, but it also results in perhaps a lack of skepticism on the part of the proponents. That must have made your work difficult. How did you account for the quality of research in your scientific reviews?
Your description of a lower standard is partially correct. I mean, many of us who were in the field were not professional scientists, or at least were not using the tools of professional scientists because the money wasn't there. I mean, for example, the work in Los Alamos I did was done under the strict rules of good science. And my work was reviewed not only at the laboratory by over a dozen people, but it was reviewed by another dozen when it went to the journal. And so the standards at Los Alamos were very high. But once the DOE said that there was no money, then the people who could continue to work had to do it outside of the normal system. Many of these people, I mean, in my case, I retired from Los Alamos for various reasons, this being one of them, and set up my own private laboratory that I built in Santa Fe. I continued my work with money from private individuals who saw the value and allowed me to continue. But I brought with me the skill and knowledge that came from having worked at a national laboratory for 34 years. Many people who continue the work did not have that background, and they did not have the tools that came from modern science. So there was a certain deterioration just on that account. But nevertheless, they did see excess energy. They did see helium. The Navy got involved. The Navy was was supportive initially because obviously if this worked, they were floating in their fuel. And so this would be a very nice source of energy for the Navy. And the Navy did some really good work. Mel Miles, for example, was one of the leaders that demonstrated that the major source of energy was coming from the production of helium. Now, when you make energy by the hot fusion program, the helium decomposes, giving off fragments of its nucleus, and that's the radiation you see. In this case, the helium does not decompose. And then that created a whole new problem. How's the energy getting out? There's no radiation. There's nothing coming out to carry the energy. So it's just heat, right? Now, people have, including myself, have measured the radiation inside the cell. And there is radiation inside the cell. It just has a characteristic and an energy that prevents it from getting outside. Now, that's fantastic from an application point of view, because you don't have to worry about being irradiated. It's really a nuisance from an investigation point of view, because the radiation provides a huge amount of energy, information about what's happening to make the energy. That riddle is gradually being solved, but it's taken a long time for that to happen. But nevertheless, the information was a mixed bag of good stuff, bad stuff. And so my reviews were an effort to identify the good stuff and show how it had a reality to it. The problem in science, of course, is that the messenger is as important as the message. And I, as a messenger, did not have as much pull as some of the skeptics did in terms of, what would you call it, reputation in the scientific field. And so a lot of what I had to say was totally ignored.
So there's been 30 years plus of attempts to get this to work, to go mainstream, to commercialize it. Lots of people, see dollar signs when they see free energy from water at room temperature. Nothing's panned out so far. It's been 30 years. This, I think, engenders some skepticism from the community. Can you tell us how the field has progressed over the years and where we're at? I mean, obviously it's been longer for hot fusion. So they haven't got anything either, and it's been a lot longer for them. So this isn't something to distinguish the two fields. But what do we know is true at this point of the low energy nuclear reactions? What can you tell us from your knowledge?
We know that Pons and Fleischmann were absolutely right. Their discovery was, in fact, valid, and it demonstrated a new mechanism for causing a nuclear reaction. In this case, it only happened within a material having certain characteristics. Hot fusion, see, the problem is that in order for fusion to happen, the two nuclei have to get close enough together that their energy states can interact. The nuclei have a positive charge, so as they get closer together, they repel one another, and it takes a lot of energy to get them close enough for them to interact. The hot fusion program does this by supplying kinetic energy to the nuclei, and so they come together, smack into each other by brute force, and that high kinetic energy overcomes the Coulomb barrier. And that kinetic energy is created in a plasma. And in order to do that, you have to put a tremendous amount of energy into the system in order to heat them up to billions of degrees in order for this reaction to take place at a reasonable rate. I mean, hot fusion is easy to cause at a low rate. I mean, you can study in the laboratory at a rate that you can detect easily. That's not the problem. The problem is getting the rate high enough that it makes useful power. And they have made enormous amounts of power, but they've never made enough to overcome what it takes to make the apparatus work, to make the plasma. Now, cold fusion, on the other hand, has a different problem. It has to also overcome the Coulomb barrier, but it does it by neutralizing the barrier as a result of electron charge. And in order to accumulate these electrons in a relationship to the nucleus that is non-chemical. Ordinary electrons have a relationship to the nucleus in the chemical context. We understand that relationship very, very well. They have to acquire a different relationship now to the nucleus that is not understood and is not seen before in nature. But apparently nature has a way of causing the structure to occur under certain conditions. And when it occurs, the Coulomb barrier is neutralized, the two nuclei come together, and they result in fusion. And that fusion produces various nuclear products. And those nuclear products now are slowly being identified. But because this is so unusual and happens within a material rather than a plasma, it's very difficult to study, and it's also very difficult to understand. I mean, physicists pretty much know how to apply mathematics to a plasma. They know how a plasma works. They know how it interacts with the nuclei. They've never had to deal with the situation that exists in the cold fusion environment, where now electrons are interacting with a nucleus in a new and totally unexpected way within a material. And so this is brand new territory, has not been explored before, is very difficult to describe mathematically. And so the normal physics technique really doesn't happen. You have to apply chemistry first, because chemistry determines whether or not you can create these special conditions. It has nothing to do with the nuclear process. And in fact, is what apparently happens is that chemistry creates these special conditions. The hydrogen nuclei and the electrons accumulate in these sites. They don't anticipate fusion. They just anticipate creating some kind of stable structure that nature has allowed them to form. And having formed that, they suddenly discovered, oh my God, we can fuse. And then the thing blows apart as a result of the energy being produced. The equivalent to the structure is ball lightning. And also a structure that was identified by Ken Shoulders many, many years ago. So we have examples in nature of the kind of structure that is occurring on a very small scale in these materials. But getting people to see that relationship has also been an uphill battle.
Now, I mean, physics is very familiar with, solid state metals, and, you can have, we know that hydrogen absorbs into metals and can occupy lattice positions, and there's going to be some shielding of the internuclear charge from the electron sea of the metal. And, this is an understood phenomenon, but it seems to be several orders of magnitude away from what you would need to create fusion. Now, there's a lot of theory or hypotheses out there as to what actually has happened. I've done a brief scan of the literature. There's people talking about hydrinos, which is a special new hydrogen atom state, like new levels of hydrogen that are lower than the currently understood ground level. There's things like hydrogen 4 that seem to require things that haven't been observed. Now, obviously, we don't know everything. We have to have some humility about what we are. But where do you stand on all of these? Do you agree with any of these hypotheses from your studies, or do you even know, or are you agnostic to these hypotheses at this point?
No. I have my own course that I enjoy better than the others. But people started trying to explain this by focusing on the crystal structure. See, palladium deuteride is a face-centered cubic structure, and the hydrogen goes into it and occupies equivalent sites within the metal lattice. And because it was happening in that structure, people initially said, well, obviously the fusion reaction is also happening in that structure. So a great deal of attention was spent trying to figure out how a chemical state involving the atoms in a crystal structure could possibly get close enough together to interact in a nuclear way. And a lot of theories were suggested as to how that might happen, and they all went down in flames. I believe that approach is doomed to failure. It is not happening in the lattice itself. It is not happening in the crystal structure. It has no relationship to the crystal structure. A different kind of structure has to be created in which a different kind of relationship between the nucleus and the electrons can form, not the one that creates the crystal structure. That relationship is well known. That's ordinary chemistry. That's been investigated for hundreds of years. So we know how those nuclei and those electrons interact. They do not interact in such a way as to produce a nuclear interaction. So there has to be a structure outside of that environment where the actual nuclear reaction is happening. Now, people have suggested a number of places where that might be. In my case, I believe it's in cracks or very small gaps, physical gaps. That is, these would be regions that would be, they got big enough, you would identify them as cracks. You could see them as gaps. But they're, in order to be nuclear active, they have to be much smaller than the ability to actually see them. They're on a 10, maybe 20 nanometer scale. And so they're essentially invisible. And so that makes it very difficult to study them. But nevertheless, there's evidence that they are there and that they play a role. Now, then the issue is, well, what grows within that environment that has the ability then to allow nuclear interaction? That structure now becomes the focus of our efforts. And I believe that structure has to have certain characteristics in order to be consistent with the behaviors that we see. And that is, it has to be a collaborative structure of many atoms. In other words, it's a supernucleus, if you wish. It's a energy state that combines the energy states of many electrons and a smaller number of hydrogen nuclei, all combined together in a stable arrangement that is stable with respect to its chemical energy, its interaction energy. But having acquired that relationship, it now discovers that nuclear states can overlap, can interact, and then that leads quite naturally to a fusion reaction, because whenever nature always wants to go to the lowest energy state, and the helium is a much lower energy state than two deuterons. So if two deuterons come together, they would prefer to make helium if they could. They can't because the nuclei can't get close enough together. They're made to get close enough together in hot fusion. Fine. So we know that once they get close enough together, they will, in fact, reduce their energy by giving it off as heat. Well, the same thing happens within this material, but by a different mechanism.
I mean, there is a lot of speculation, as you might imagine. So you're talking about chemical clusters of hydrogen or deuterium atoms and electrons forming in these cracks and having an overlap with some nuclear structure. And it's well known, I would say, that low energy nuclear resonance states are not well understood. There's a lot of uncertainty in whether there are such things available, and it's very likely that there's some evidence, I think, from this Google study. Actually, they were looking at palladium wires, I think, and finding some interesting nuclear dynamics happening. So that, I think, comes to mind correctly. Do you have what support do you have for this model that you're putting together? Is it something that's been published, or is it something that you just picture and you're contemplating personally?
Well, I have, how would I put it? I have two sources of energy. One is the literature itself, and I've read practically every paper and analyzed practically every effort. So I have available to me information that most people don't have in terms of what is known from other sources. I probably have the most complete bibliography in EndNote, so that I can search it very conveniently. And so I have the world's knowledge accessible, and so I use that. And the other is that I'm doing experimental work in my own laboratory. And so I can actually see what happens with my own eyes as a result of doing various things that I anticipate having some benefit. By combining that information, I come to a conclusion. Now, that conclusion is not shared by many other people, because most people don't have that collection of knowledge and that collection of understanding, to some extent because a lot of what I've done in the laboratory is not published or is not easily available. So I come to a conclusion, and I hope that conclusion is close to reality. And I tell anybody that wish to know what my conclusions are, I'm perfectly happy to tell you. But now explaining or justifying them becomes more complicated, because now you have to understand what's known, and that takes some difficulty in explaining, and then you have to understand what I've done and seen. Well, that takes probably an hour to explain. So justifying in a conversation such as this is practically impossible. You can just have to say, well, okay, this guy has a whole bunch of information that he's gotten a whole bunch of different ways, and he's come to this conclusion, and he's an honest scientist trying to figure this out. So maybe we'll give him the benefit of the doubt.
Yeah, I mean, certainly, I'm open to new ideas and looking forward to learning more as I explore this field a little bit. And I certainly don't have your depth of background in the necessary chemistry or even the physics here. And, as you say, there are things like ball lightning that are poorly explained by known science. Another one that comes to mind in this field is the single bubble sonoluminescence experiments. People have looked at, you can make bubbles cavitate in solution using sound waves, and you can measure X-rays coming out of them. These things are little tiny accelerators. As the bubbles collapse, they're creating huge pressures and temperatures at the core of the bubbles. And maybe that, I like to speculate that maybe that has something to do with it. And probably this crack propagation mechanism may have similar physics associated with it. So I'm open to poorly understood phenomena being at the root of this, because we know that they exist. It's not something that, it's not picking out of the air. But
well, I mean, the sonoluminescence, that produces hot fusion. That's not cold fusion. Hot fusion can be also made by bombarding a material containing deuterium with energetic deuterons. That also makes hot fusion occur. That's not cold fusion. You can also make hot fusion occur by what's called fractal fusion. When cracks form in a material containing deuterium, there's enough voltage created across the crack to accelerate the deuterons to a high enough energy so that a few of them will fuse. And because hot fusion is very easy to detect, thanks to the neutrons, you can detect it to occur at very, very low rates. That happens during cold fusion. People see neutrons occasionally being given off during cold fusion when neutrons should not be produced, and these are being produced by what's called fractal fusion.
You're confident that the observations that are being made in low energy nuclear reactions are not hot fusion, because you're not detecting the neutron flux, but you are detecting the heat. So there's a delta there that's unexplained by hot fusion. Is that the basis of that conclusion?
That's right. The amount of heat that's coming off is far in excess of any possible chemical source. So therefore, it must have a nuclear source. There aren't many nuclear sources available. And then, at the same time, it's not making any radiation, which a nuclear source is expected to make. So that's what makes it so unique.
Now, you've mentioned that you measured the radiation in the cells. What have you measured?
Well, I've measured initially the emission of hydrogen. When you create the LENR effect by gas discharge, you can measure what's coming off as a result of that with a silicon barrier detector. And I measured the emissions and studied them with respect to how they respond when you put an absorber in front of them. And the emissions that I measured were ions coming off. And ions have the characteristic that when they pass through a material, they lose some energy, and then they exit on the other side of the material with less energy, but they're still there. And so what you do is see a shift in energy. The magnitude of that shift tells you the nature of that material, whatever it is the ion is. We anticipated the ion to be helium coming off, because that's what you see in the gas after you've allowed this energy to be made for a while. I did not see helium. It was not helium. I could tell that it was not helium by its response to the absorber. It was an isotope of hydrogen. Now, the question is, which isotope of hydrogen? We know of three. There's light hydrogen, which is a nude proton. There's deuterium, which is a proton and a neutron. And there's tritium, which is a proton and two neutrons. None of those are being made. And so therefore, what were we seeing that would end up making helium in the long run? Because we do in fact see helium in the long run. Well, the only possibility is hydrogen-4, and that then this hydrogen-4 then decomposes, that is, turns into helium by beta emission, just like tritium turns into helium-3 by beta emission. Hydrogen-4 turns into helium-4 by beta emission. That is the assumption and the assertion that I've made based upon that information. And then once you start down that road, you come to a lot of other logical conclusions about how the other nuclei of hydrogen will interact, because deuterium was the original isotope of hydrogen that worked. But then they didn't expect ordinary hydrogen to work. But now they discovered that ordinary hydrogen works just as easily as deuterium does. And so how's that possible? And then how can you make helium-4 and tritium also without neutrons? I can explain all that. And all that comes from a logical relationship to this original work. And now, recently, Frank Gordon discovered that when LENR occurs, electrons are emitted, electrons having significant energy. You would not see those easily, even in the cell itself. And it turns out he used a very clever technique, but a very standard technique, which is cleverly used to show that these electrons were being emitted. And that's where the rest of the energy is. The energy of the hydrogen-4 coming out is only a small fraction of the total energy that's being generated each time a hydrogen-4 is produced. So something else is carrying that energy. He found that the something else were electrons. Before that, people thought it was photons. And it's not photons, it's electrons.
I've heard some discussion about the hydrogen-4 hypothesis. It has been published a bit. There's a couple questions that critics brought up about this idea. One is why has no one else seen hydrogen-4? The other is that high energy electrons, I think they were saying something like 27 mega electron volts for the electron coming out of this reaction, is what's being proposed, which is very high energy and should, I assume, create gamma rays when it interacts with material, which would be measurable. How would you respond to those criticisms?
Well, the first criticism of hydrogen-4 was that when they made hydrogen-4 like normal techniques, which is bombarding deuterons, very high energy, sometimes bombarding lithium. But in any case, they had a very brief nuclei that is identified as hydrogen-4, but it very quickly decomposes by giving off a neutron. And so the assertion is that reaction occurs in the LENR environment also. And so therefore, this cannot possibly be the explanation. My assertion is that the LENR environment is so different from the way in which they made it in the past, causing the neutron, that that the high energy experience doesn't apply. That the hydrogen-4 can be made at low energy in the LENR environment, and when it does so, it acts like tritium. It just simply decomposes by beta emission to the helium-4. I mean, we have to have something that makes helium-4. We know that helium-4 is being made. We have to have something that's not helium coming out. So we're stuck with a problem of how to reconcile those two observations. The only way of reconciling them is hydrogen-4 coming out, and then it decomposes very quickly by beta emission. We don't see the beta. Now, we don't know what the beta energy is. People could calculate the beta energy all day, and it would not necessarily have any relationship to reality. At this point, we just don't know enough about hydrogen-4 to be able to make such a calculation accurately. So I'm relying on the fact that we have a logical conflict, and somehow or another we have to resolve that logical conflict. The idea of hydrogen-4 allows that conflict to be resolved, provided you make these few assumptions. We'll wait to see if these assumptions are right or not.
Okay, interesting. So you have a hypothesis, you have experiments that seem to be much more reproducible now. You mentioned the quality of the material is key to getting reproducibility. Can you discuss that just a little bit so that we understand why, originally just any palladium didn't work, and now you're confident that you can get reproducible results? This is something you say you've been working on. Just maybe expand a bit on that, please.
Well, early in the field, people who had success did so using a batch of palladium. And then when they would use another piece of that batch, they discovered that would make success also. I mean, just to give you an example of my personal experience, after the DOE shut down the laboratory officially, working on cold fusion, I continued to work, and I persuaded the administrators in my division to give me some money to build a calorimeter to test the LENR. The laboratory at that time had the ability to defy the DOE to some extent, and so I took advantage of that. So I had a calorimeter. Now, then the question is, what do I run? Well, Takahashi in Japan was having fantastic success reproducing the LENR reaction. And in his case, he was measuring neutrons. Why he was seeing neutrons is an entirely different issue, but nevertheless, he was also seeing some heat. And he agreed to send me a piece of the batch that he had made from which he was getting his samples. And he also sent pieces to other laboratories. I put that piece in my calorimeter, and it made excess energy. It was the first sample I ran, and it made significant excess energy. So that was exciting for me, and it also demonstrated that the characteristics of the material were maintained through the entire batch, not just an individual sample. So, and then other people, laboratory in Canada, another one in Italy, also got excess energy from samples that he supplied. Well, then we ran out. So Takahashi went back to Tanaka Metals in Japan, who supplied this, and said, here, I want another piece. And they made him another piece. And he sent me a piece of that batch. It was dead. No excess energy. And he couldn't see any either. So he went back to Tanaka Metals and he said, look, hey, I wanted the same stuff. What the heck went on here? And they said, well, yeah, I mean, this is a special thing. I mean, they make tons of the stuff. This was just a special little treat for him. And so they did it a different way, a little bit cheaper than the first sample. And he said, no, I want it exactly the same way. So they made a third sample exactly the same way. He sent me a piece of that, and it made excess energy. Akubri also, early in the field, was working with material having no success whatsoever. He got a spool of wire from Goodfellow, which is a company that reprocesses palladium and sells it. In this case, it was a wire, and he put it in his calorimeter. And almost every piece made excess energy. He did some fantastic work, got a lot of detail as a result of that batch. Once the batch was used up and he started using ordinary palladium, it didn't work. So something was done to the palladium that was maintained throughout the entire batch. And that had to happen at the process of manufacture. Not anything was done subsequent to that. And it had to survive the treatment, that is, turning into a plate or turning into a wire or turning into whatever physical form a person was given. It still worked. Why? How could that possibly be explained? Well, my explanation is that the original material had small particles of impurity, probably various oxides, that came with the palladium. And and the final treatment of the palladium, after it's separated from the other elements, is for it to be melted. So it forms a solid material that can, by mechanical means, be turned into wire or plate. But during the melting process, any particles that are in there will float to the surface because they have a lower density than palladium, unless they're very tiny. The smaller the particle, the less opportunity for it to float to the surface. So to the extent that these fine particles exist, were maintained, and they would be distributed in a random way throughout the material, that has the potential to create the gaps. And it does so by when the palladium is reacted with deuterium. When palladium reacts with deuterium, it expands. And a particle contained in the palladium doesn't expand, it's inert. The palladium around it expands, leaving a gap between it and the surrounding palladium deuteride. If I claim that if that gap has a critical size, it can then host the necessary structure that leads to the reaction, the nuclear reaction. Now, to test that, I have added particles of various sizes to palladium and found that, in fact, the ability to make it work is sensitive to the size of the particle I added. And it doesn't matter which particle. I mean, I can use silicon dioxide, magnesium, or calcium oxide, boron nitride. All of these are materials that have a melting point in excess of melting point of palladium. So they are maintained as a solid particle within the melt. And so I have evidence that shows that, in fact, that is the cause of batches of material being active. And now I can make batches on purpose by adding particles of a suitable size.
That's very interesting. So there seems to be, you're claiming that there's reproducibility now on the effects of creating excess heat from the low energy nuclear reactions. There's no damaging radiation that comes off of these things. So we're back to the point of panacea here in energy production. When should we expect to be producing commercial amounts of energy from this process and Nobel Prizes to be awarded?
Well, that's going to be a while. You have two problems. One is the general scientific profession still is unsympathetic, and therefore the source of money to do suitable research is not available. The second is that within the field itself, there is a reluctance to believe some of the new ideas that I'm advocating. And the third is that we really don't understand how it works. I mean, yeah, I can tell you how I can make a little bit of excess energy happen with much greater reproducibility, and that's very useful for research purposes. But it's absolutely useless it's not information that is known that can amplify the effect to levels that would make useful power. I mean, right now I'm working at levels of a few watts of of energy from a small sample. I mean, even if you made the samples enormously larger, you still would not have a practical generator. We have to understand the nature of this structure that is the actual site of the nuclear reaction and how to make that structure occur at high concentration. Right now, it's occurring at a very low concentration and a very variable concentration, depending upon what I do and what. With each sample, I mean, I can make it happen, but each sample is different. Each sample will produce a different amount of energy. So I cannot predictably make a sample that has the ability to make enough energy, make it attractive as a source. Now, some people have materials and they have treatments that are producing enough power that they are on the borderline of being practical. But until we understand the mechanism and how it works, not only can't it be made practical, but it will not be made legal, because nobody's going to give permission for a nuclear process to be operated throughout society that they don't understand, because that understanding could very easily lead to a nuclear explosion or some other unanticipated consequence. So the regulators, the cautious people who are trying to protect society, will simply not allow this to be used on a large scale unless it can be proven to be totally harmless.
Yeah, I certainly have experience with regulations being overzealous in the matter of nuclear energy.
Well, yeah, I mean, we paid a price for that ignorance with fission energy. We discovered by terrible experience the consequence of obvious mistakes and or natural consequences when that particular method is used. This particular source of energy doesn't have that characteristic. You can't make a bomb out of it. On the one hand, that's very good. On the other hand, it eliminates a lot of interest in the mechanism. So we have a lot of work to do. Now, for that work to be done, a significant amount of money has to be applied. I mean, after all, fission energy required the Manhattan Project to get it all into a form of usefulness, first as a bomb and then later as a sort of power.
I think the reproducibility would go a long ways towards interesting mainstream science. I mean, that was what drove them away at first, was the fact that it seemed magical and not reproducible. So if we can get something that's at least reproducible, we have enough of a handle on it that you can do good research, I think, and move forward. So I think that, that it's hopeful that major journals are starting to publish some of these results. The Nature Perspectives article by Google researchers recently shows that there is some appetite for reinvestigating the claims, although I guess they weren't successful. Is that correct? In reproducing the cold fusion effect?
They were not successful in reproducing it. I mean, I worked with Google at the time, so I'm knowledgeable about what went on. They were not. They were interested in trying a variety of different materials that either were suggested that might work or had worked in the past. They were not interested in investigating this from a basic science point of view. They were hoping that these materials that they chose and that some of they supplied to me to look at would work. And just a random collection of materials obviously doesn't work. I mean, that's not the way to go about doing it. And so it was not unexpected that their efforts failed. But nevertheless, it got them interested. Carl Page, for example, has gotten very interested in this and was very instrumental in organizing ICCF 24 in California, where he brought the attention to a lot of conventional supporters outside of cold fusion, and is working to encourage financial support and further work in the field. And that's what it takes. You somehow or another have to encourage people who have the money and who have the influence, the political power, to work on something at the scale that's required to understand something so complex as cold fusion. And he's working to have that happen, and that's fantastic. And that will certainly amplify and accelerate the ability to make this work. But we still have a lot of work to do.
Well, that's, I think, a good place to end our interview on. I appreciate you taking your time to come and chat with us and explain your history and research in this field and help us to understand what's really going on, because it doesn't have a lot of light being shone on it from mainstream science. So I think it's good that we're driving these things to ground and figuring out what really is happening here. So I appreciate you coming on. Thank you so much, Dr. Storms. If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patron.podbean.com/therationalview. Thanks for listening.